Welcome back to another video about complex numbers. This time we're going to define and do some examples of the argument of a complex number. So look on the left side of the screen here, and I've plotted the point 3 plus 3i. That's a complex number. We plot it as a point in the complex number plane, going out 3 on the real axis and then up 3 on the imaginary axis. In the last video we talked about how we can compute the modulus of this complex number just by using the Pythagorean theorem. And that modulus would tell us the distance away from the origin that that complex number is. Now, another quantity that would help us locate that complex number in the plane is, in addition to the modulus, would be to know the angle that I create right here between that complex number and the positive real axis. Let's call that angle theta. You can see here that the theta here is going to be 45 degrees, or pi over 4 radians. We'll keep it all in radian mode from here on out because it goes an equal amount out on the real axis as it does up on the imaginary axis. It creates a 45-degree angle, and that's pi over 4 radians. So that angle is pretty important, and so we're going to give it a special name. The argument of a complex number over here, of a complex number z equals a plus bi, is defined to be the angle made by that number and the positive real axis. Positive real axis. And the notation here is arg of z. So the argument of a complex number is the angle that's made by the number and the positive real axis. And by the angle between a number and the real axis, what I mean is if you take the number and connect it back to the origin with a line segment, it's the angle that's made by that line segment and the positive real axis. So for example, as you see here, the argument of the number 3 plus 3i is pi over 4. But let's look at several more examples to get the idea. So we've already seen that the argument of 3 plus 3i is pi over 4. What's the argument of negative 4? That's the same thing as negative 4 plus 0i if you want. That's a number that sits on the negative real axis. So it's 1, 2, 3, 4 right there. There's negative 4. What is the angle that's made between this number, negative 4, and the positive real axis? So that is a 180-degree angle, and so its argument is pi radians. So the argument of negative 4 is pi. Likewise, the argument of any number on the positive real axis would be 0, because that makes an angle of 0 with the positive real axis. What about 3i? Well, 3i sticks straight up on the imaginary axis, like so. And so what's the angle that is made by it and the positive real axis? So that would be a 90-degree angle, and so its argument is pi over 2. What about negative 1 minus I? Well, let's see, where is that going to be located? It's kind of hard to see because the grids are small, but that would be right here. I go back 1 on the real axis and down 1 on the imaginary axis. So right there is negative 1 minus I. Now, if I connect this with a line segment, I'm asking, what is the angle that's made between it and the positive real axis? If I start here and rotate all the way around, how much of an angle is that? Well, it's pi radians, 180 degrees, plus an extra 45. So that's 225 degrees, also known as, if I switch into radian mode, that's pi radians plus an additional pi over 4 radians. That is 5 pi over 4 radians. Again, we typically keep all this in radian mode throughout, so you can think in degrees if you want to, but answers need to be in radian mode. So what about complex numbers that aren't so geometrically nice? So all those we're fairly quickly able to decide what the argument was because the angles worked out nicely. What about something like 3 plus 5i? How do you get to that? Well, let me do some erasing here. And 3 plus 5i is going to be located here in the first quadrant. I'll just clear out that first quadrant. 3 on the real axis and 5 on the imaginary axis. So there is the number 3 plus 5i. Let me just connect that back to the origin with a line segment. And I'm wanting to know, what is that angle right there? Well, that's not a really simple angle that trigonometry would let us get into very easily. So let's kind of think about how we would do this. Well, I do see that I'm creating a right triangle here. And this leg length has length 5, and this leg has length 3, and I'm really interested in this angle that's inside here. So I can use some trigonometry here. If I remember my SOHCAHTOA, I know that the tangent of the angle that I'm looking for right there is equal to the opposite over the adjacent angle. So I don't know what the angle is, but its tangent is 5/3. Well, if the tangent of the angle is 5/3, then the angle itself would be the inverse tangent or arctangent of 5/3. Okay, and so that's going to be my argument in this case. It's the inverse tangent, or you might know it as the arctangent of 5/3. Numerically, that's about equal to 1.0304 radians. So we have something of a formula by which we can calculate the arguments of angles if I know what the real and imaginary part of my complex number actually was. For example, let's look at 1 minus radical 3i. Now where is that? I'm going to switch to blue here and let's plot it. So 1 minus radical 3i, that goes out 1 on the real axis and down a little ways on the imaginary axis. This is getting crowded here. Let me just draw a little blown up version of this right here. So I would have to go out 1 here and down radical 3. Radical 3 is about 1.7-ish. So it's down a little farther, radical 3, and that point would be located right there. So what kind of angle does that make with the positive axis right there? Well, if you notice, this is a 60-30-90 triangle because, so let's think about how I could compute the argument of that complex number. That's the angle right here. Well, let's see. This is a length of radical 3, and this here is a length of 1. And so the tangent of that angle, the tangent of the angle that I seek, is equal to square root of 3 over 1, which is the same thing as square root of 3. So theta is equal to the inverse tangent of radical 3. And the inverse tangent of radical 3, if you consult your calculator or Mathematica or just your trig knowledge, it will tell you that the answer is pi over 3, which is 60 degrees. Now that looks right. If you look at the angle that's being formed here, that looks like a 60-degree angle right there. However, the argument of this complex number is not actually pi over 3, it's negative pi over 3. And that's because the angle is going this way, it's going clockwise, and so I have to put a negative sign on there. Or I could also say that it is 5 pi over 3. Those are equivalent angles. The point being that if you use the inverse tangent to try to calculate the argument of a complex number, to try to get this angle, you'll get a number for this, but that number might refer to an angle that's in the wrong quadrant. So this is a typical problem that happens when dealing with inverse trigonometric functions. Just make sure that if you use the inverse tangent to find the argument of a complex number, actually look at where the complex number is located. And if the argument that you get out of the inverse tangent doesn't actually match the actual location, you might have to mess with the signs or the shifting of the angle that you get to make it exactly right. So that's a brief description of the argument of a complex number. It, together with the modulus and its conjugate, give an almost complete description of a complex number, as we will play with in class.